Hello. Um, in the previous lecture, excuse me, in the previous lecture, we introduced ridge regression, the constraint formulation of ridge regression, and then the Lagrangian form. So I recommend that um, if you just to review this from the previous lecture, the relationship between t and lambda, so you understand that, and the same thing for lasso regression. So one thing I want to say is that I'm emphasizing this. The value of lambda itself, um, which will be which can be determined using cross validation, um, only matters as much as we care about beta hat. So the value of lambda itself doesn't have any meaning for us. Once we find the lambda that minimizes cross validation, we just plug it in here and we use it to get our beta hat. But we do not make any interpretation about lambda, the value of it's not really important. The value, the lambda that minimizes the cross validation is important, but we do not interpret it. For example, when we estimate beta hat, the coefficients of beta hat, they have meaning for us. They tell us more or less the association between the response and the corresponding feature. How much one unit increase in this feature will lead to how much increase in the typical increase in the response. That's what I mean by interpretation. So the values of the coefficients of beta hat allow us to make some interpretation, but the value of lambda is not as such. And the same applies for ridge regression. Okay, so let's just review a few reasons why we are considering an alternative to least squares. Um, because least squares has often low bias and high variance. Um, and it turns out that by adding a little bit more bias, which means shrinking the coefficients, making it a little bit smaller, which Ridge is doing, or setting some coefficients to 0, we can increase the prediction accuracy, because typically we have too many predictors. Too many predictors, too little observations, and we have problems you are pretty familiar with. Also, when we set some coefficients to 0, which obviously is not just any coefficients that are or that seem not to be associated with the response, then we are able to identify a smaller subset. Um, and why is that useful? Because we have a simpler explanation for the relationship, parsimony. Now, what is the effect of lambda? What is the effect of lambda on the coefficients? Um, for example, for ridge regression. What are we looking at? We are looking at this graph here. On the horizontal axis, we have lambda from small values to large values. And then on the vertical axis, we have standardized coefficients, which are the estimated coefficients divided by the standard deviations. Okay, so what is a standardized coefficient again? It's a regression coefficients that we get, and then we divide them by the standard deviation of what? Of the corresponding feature. Why is that something we do? Again, because different predictors may have different scales. Not they may not. They typically have different scales. For example, the scale of rating and income and credit limit is different. So the estimated coefficients for each of them will depend on the scaling, and in order to have a way to compare these different coefficients, we divide them. So we divide the coefficient for income by the standard deviation of the income. So we divide the coefficient for limit by the standard deviation. So these are the standardized coefficients, and they're unitless. That's why they're comparable. So what are we seeing here? We see this red line here, which refers to limit. Then we have rating, we have student, and then we have income, which is this one. And then we have these gray lines. These gray lines represent many more coefficients used. So So at the extreme left-hand side of the plot, lambda is very small. It's essentially 0. So when lambda is 0, the corresponding ridge coefficient estimates are the same as the usual least square estimates. Remember, if when lambda is 0, then we don't have this term, so we are solving the least square problem. But as we increase lambda from a very small value to a larger value, especially at the very extreme, so when lambda is extremely large, then all the ridge coefficient estimates are basically 0. And this is the null model. This is the model which is only an intercept. Now the interesting regime is in between these two extremes. And what we see is that as we increase lambda, the ridge coefficient estimates tend to decrease. Now here we have rating which slightly increases and then decreases. So you may say, why is that increasing? Isn't that supposed to shrink it? Yes, it is supposed to shrink it. The issue is that we have these many different coefficients that are interacting with each other. So if the role of limit comes down, maybe that will lead to the role of rating increase. But overall, the pattern, the big picture pattern is that yes, even though that this goes up, overall the big picture pattern is that as we increase lambda, the coefficients tend to decrease. That's why we call shrinkage. We are shrinking them towards 0. Well, shrinking towards 0 doesn't mean that we make them 0, like 400 can become 300. So they're getting closer, but that shrinking creates stability. And it adds bias, but it reduces the variance. And when we are in a regime where we have many features, not many observations, we can easily suffer from overfitting, and this is a way to avoid that. Now on the right hand side, on the right hand panel of this figure, we are seeing the same coefficients. We have income, limit, rating, and student. This is income. We have limit and rating, and then we have where the student, where the status is student. But on the horizontal axis, instead of displaying lambda, we have the L2 norm of the ridge estimate divided by the L2 norm of the least square estimate. Okay. Now you may say, what is that? What is that supposed to mean? Okay, let's think about it. When this ratio is 1, it means that the L2 norms are the same. And if the L2 norms are the same, when are the L2 norms are the same? Well, when the ridge regression estimate is least squares. So for lambda equals 0, the ridge regression coefficient estimate is the same as the least square estimate. And therefore, their L2 norms are the same. So this ratio being equal to 1 refers to lambda being almost 0, somewhere around here. And you see that the value of the income at this point is the same as the value of the income at this point. The value of the status, the coefficient for student is the same. Rating is the same, and limit is the same. Okay. So now what about here? This ratio is 0, meaning that the beta hat regression coefficients are 0, meaning that lambda is infinity, and we are here. So in a way, why is this useful? Why is this something we like? Because it essentially, instead of plotting everything in terms of lambda, we can think of the x-axis here as the amount that ridge regression coefficient estimates have been shrunken towards 0. So as we go from right to left here, we are going from left to right here. So these two are telling the same story. One is in terms of the amount that the ridge regression coefficient estimates have been shrunken towards 0. And the other one in terms of lambda. Okay. Okay. So this is ridge regression. Okay. So ridge regularization um, typically has this form. Sometimes you may see 1 over 2 here, or 1 over 2n here, or you will see scaling here, but all of them are ridge regularization. They're all trying to balance the residual sum of squares with the L2 norm. That's all that matters. The rest is just a scaling. Okay. Now, The question that I like to answer for the rest of this lecture is how can we find this estimate? Is there an analytical formula for this, the same way that there was a formula for um, least squares for linear regression? Is there such a formula or not? Can we can we formulate this problem as a least square problem? So we use our knowledge of least squares to apply it to ridge regression? And the answer, obviously, the way I ask it is positive. The key is to define these two new quantities, x tilde and y tilde. We put this matrix X here, so we have this block matrix. We have one block X, it has n rows, p columns, and then we have this identity matrix here multiplied by the square root of lambda. The identity is a p by p matrix, so this is p by p, this is n by p, making x tilde n plus p times p. X tilde has n plus p rows and p columns. Y tilde is y and then filled with zeros at the bottom. So it's a block vector. So we have one block y and we have one block 0. So it's n plus p rows and one column. And then the question is there a way to formulate ridge regression problem as a least squares problem in terms of x tilde and y tilde? That's the objective of the rest of the lecture. Y tilde minus x tilde beta L2 norm is essentially just y and 0 minus x beta square root of lambda beta. Why? Because if you multiply beta by x tilde, you have x beta, which you have here, and then beta times the identity gives you just the square root of lambda beta. So you see what's happening from here to here. So the L2 norm of this vector is the inner product. L2 norm squared is that vector inner product with itself. So this column vector, here we have a row vector, here we have a column vector, and the inner product is just y minus x beta transpose negative lambda beta transpose y minus x beta minus lambda square root of lambda beta. This will get inner product with this term, and then the negative square root of lambda beta transpose gets inner product with negative lambda negative square root of lambda beta. So we have y minus x beta transpose times y minus x beta, and then we have square root of lambda times square root of lambda gives us lambda. So we end up with lambda beta transpose beta. So what do we end up with? Y minus x beta L2 norm plus lambda of the L2 norm of beta. To summarize, what we did was to show that the L2 norm of y minus x beta plus lambda, the L2 norm, so there's a 2 missing here, there's a 2 missing here, is the L2 norm of y tilde x tilde beta minus x tilde beta. Now that's interesting because essentially the ridge regularization cost function is the cost function of linear regression, simple, not simple, but multiple linear regression or least squares, in a transform for the transformed design matrix or feature matrix, and a transformed response. I mean, it's not really transformed, but yeah, it is transformed. It is something different. Now, obviously, what we can do is we can use our knowledge from least squares to solve a ridge regression problem. So just to clarify, this is ridge, and since these two are the same, so we can minimize this over beta or minimize this over beta, and the answer will be the same, and we know what is the answer to this problem. It's just x tilde transpose x tilde problem here. That's not a transpose. That is an inverse. So I'm going to fix that. It will take some time before it kicks in, but I'll also change the color so you know these were errors. Apparently that's what good archaeologists do too, when not archaeologists, but those who work in when there's an old building from 1,000 years ago and there are cracks in the wall and they want to fix it. The point is that the cracks should be filled in a way. There are different schools of thought that the cracks in the wall should be filled in such a way that when somebody comes and sees it, can recognize what is the original piece, what is the original part of this building or wall or whatever monument you're looking at, and what is added today. But I mean, not everybody adheres to this standard, so let us adhere here to this. I will there will be a red 2 here in the notes, and this will be -1. Okay. And where this is coming, this is from the least square problem. This is great because we solved the problem using something we knew from before. Now let's try to simplify this. Just to refresh the memory, X tilde was this block matrix. Y tilde was this block vector. So X tilde transpose X tilde is so we have to multiply this by this and this by this. So X tilde transpose X tilde is X transpose X plus lambda I. What about X tilde transpose Y tilde? gives us x transpose y plus this multiplied by 0. So we end up with x transpose y. So we substitute here what we have, and we substitute here what we have. So the beta hat ridge regression coefficient estimate is x transpose x plus lambda I inverse x transpose y. And when lambda is 0, we get back to the least squares estimate. So a question that we should have been asking ourselves is x tilde transpose x tilde invertible or not? That's a question we should be asking ourselves. Or under what condition is it? Okay, this is not corrected, but it's okay. For lambda greater than 0, is x tilde transpose x tilde invertible? Yes or no? No. Let's look at x tilde. It's a block matrix. It has n plus p rows, p columns. Number of rows n plus p, number of columns p. Is this matrix full rank? That's the first question we should be asking ourselves. And full rank means that are the columns of x tilde linearly independent? Can we find a non-zero vector v such that x tilde v is 0? If we can't find that, then what does that mean? It means that the columns are linearly dependent. Well, what is x tilde v? X tilde v is xv square root of lambda v. Is it possible for this vector to be 0? This vector has two block vectors, is made out of two block vectors. When in order for this to be 0, it means that xv must be 0 and the square root of lambda v must be 0. If v is non-zero, then square root of lambda v is also non-zero. Then for non-zero v, xv cannot be 0. Therefore, the columns of x tilde are linearly independent, and since the number of rows is larger than the number of columns, x tilde transpose x tilde, again, there should be a tilde, that's another mistake, let me fix that. Then this also is invertible. So the conclusion is that for lambda greater than 0, this is always invertible. So as long as lambda is not 0, even if it's a tiny, tiny, tiny small positive number, we have a ridge regression coefficient estimate. So remember the public health data? And remember we had some problems here. So let me just run it from the beginning. Okay, always remember to set the working directory to source file location. Okay, so you have this problem. Now let's say lambda LR, so this is lambda which is 10 to the power of -3, tiny bit, right? And then we have beta hat R is this, right? Now, now what do we need here to make this ridge? I need to add a lambda identity. Lambda identity. So you see this lambda identity. All I need is to add this here. And this identity, what are the dimensions of it? Say I is equal to the diagonal matrix, right? Filled with ones, p and 1. Does it work? I don't know. Let's see. P is 127. So what's the problem with this? Sorry, ones. I'm mixing different languages, and we don't have ones here. Okay, and I'm mixing MATLAB. So we have rep 110. So we repeat that. Okay. So I need rep 1 p. That's it. So for example, diag rep 1 3. We got. So we add this here, and then we have LR identity. Okay. So let's see. Now we don't have any we don't have the previous problem. We have estimates for all the coefficients. Let's just change lambda. We have increased lambda, and you see all the numbers now are significantly smaller than 0, right? Now the thing is that, yes, as we increase lambda, the coefficients get smaller and smaller, but they are never clamped to 0. None of them is exactly 0. They're always going to be slightly different from 0, but not exactly. As opposed to this, which is significantly Now, when lambda gets too small, then we will get back to the problem. It's almost singular, so we have to start 10 to the power negative 6 is probably too small. Let's see if 2 times. Okay, that works. And you know, now they are bigger. The coefficients are bigger. So this is ridge regression. Now lasso behaves slightly different. Not slightly, and way different. What is similar between lasso and ridge is that as we increase lambda, the coefficients get shrunken, but unlike ridge, which just goes and slowly gets smaller and smaller and smaller and smaller, you see it never is zero. It just gets smaller and smaller. For lasso, if you increase lambda enough, the coefficients get clamped to zero. Boom, it hits zero. That's a fundamental difference between lasso and ridge. On this side, what are we looking at is these are the contour plots of least squares. I mean, remember that ridge regression coefficients solve what problem? Minimize the residual sum of squares subject to this constraint. And what is this constraint? This is a circle. This is a sphere. In 2 dimensions, it's a circle. And more than 2, it's a 3 dimension is a sphere. And more than that, it's a hypersphere. Essentially, we're saying that the betas, if it's a vector, should be within a sphere of radius square root of t. So we're saying take the origin, draw a hypersphere around it with radius square root of t, and within that hypersphere find the beta that gives us the smallest residual sum of squares. So this beta hat is, assuming it exists, this beta hat, assuming it exists, is the least square estimate. And as we get farther away from it, the residual sum of square increases. So the residual sum of square over all So this is a problem with two coefficients. So the residual sum of square is constant over these contour plots. So for all the combinations of beta 2 and beta 1, all the combinations of beta 2 and beta 1 on this ellipse, says the residual sum of square is constant. The further we get away from beta hat, the residual sum of square increases. So the residual sum of squares here is less than the residual sum of squares here. And the residual sum of squares for all the combinations of beta 2 and beta 1 are less than the residual sum of squares here. Now, if we had no constraint, we would end up with beta hat, which is our least square estimate. But because we have a constraint, the constraint saying that beta 1 square plus beta 2 square should be less than equal than S, where S here is T square. This S is our T. This S is our T. This S is this T. So since we are saying that we are looking for the best, for the coefficients, beta coefficients within this circle that minimizes the residual sum of square, it happens that it will touch it somewhere in the boundary. Unless this point is inside, which if this beta hat is inside here to begin with, then the constraint is redundant. So if you increase the S large enough to encompass this least square estimate, assuming it exists, then this constraint is not active. But the whole point is that we want it to be active, so it will be touched somewhere here. So we see that the shrinkage is happening. So from a least square estimate here, we end up with an estimate which is here. So beta 1 from here goes to here, the shrinking. Beta 2 from here goes to here, shrinkage. Now in the next video lecture, we will focus on L1 regularization, and we will speak a little bit more about how L1 is functioning and how L1 leads to sparsity. And sparsity for us means that the most of the coefficients, estimated coefficients, are 0.